All right, so welcome back. Lecture number 2 for chapter 14. So now we're going to talk about how some reactions might happen in just one single step, and some of them take multiple steps for them to occur. So far we've been talking about elementary reactions, but now we want to kind of dive down a little bit more deeply. So our individual molecules here, they can undergo two different types of reactions. They can undergo reactions that are called unimolecular. So unimolecular reactions, this is where a single particle or molecule or ion, one thing, rearranges into one or two different particles. Okay, so we have one thing and then it's going to go into one or two. Okay? Or it could be a bimolecular. So bimolecular reactions are where two particles collide and rearrange. So single would be A going to B, or A going to B plus C. This would be where you start with A plus B, and this could go to just one thing, like C, or it can go to C plus D, where it rearranges, something like that. Both of these type of reactions are what we call elementary. So these are elementary reactions. What actually occurs at the nanoscale. But what we might see is different. So what we see, what we observe, what's at the macro scale might be different. So we could see one of two things. We could see exactly one of these processes occurring. It's just straight up a unimolecular reaction or straight up a bimolecular reaction. So we could just directly see this elementary reaction. It directly occurs by one of these two processes. And when we say one of these two processes, we're talking about unimolecular or bimolecular. So it occurs just one of those two ways. And that's how you've been thinking about reactions so far. This plus this reacts and makes this in one fatal swoop. But you need to expand your thought and start thinking about how some reactions, when they go from your reactants to products, it doesn't just happen in one step, but it's a series of steps. And this is called a complex reaction. So far all you've been thinking about have been these elementary reactions, but now we're going to expand to include complex reactions. All right, so when we're talking about our elementary reactions, these are the simple ones. These can occur as written, so A plus B, or A going to B plus C. Like, we can just write them out as normal. And their rate laws are predictable. So unimolecular reactions are always going to be first order, and bimolecular reactions are going to be second order. First order because there's only one thing, second order because there's two things, uni and bi. So those are the easy ones that we've done pretty much this whole chapter thus far have been elementary reactions. That's what we've been working with so far this semester in this chapter. Complex reactions do not occur as written. We say A plus B goes to C plus D, but it's not just this one step right here. Really, there's a lot going on that has to happen to these before we get those. So they're going to progress by a series of my elementary steps. It's going to take a couple of times before I can get to my end product. So let's look at an example. So here's a complex reaction. We've got 2I reacting with H2O2 and 2 H3O pluses to make I2 plus 4 H2O. Okay? And they're going to tell me that this works when my concentration of H3O plus is between 10 to the negative third molar and 10 to the negative 5 molar. And here's my rate law. So they gave me my rate law. Now, how do we know this has to be complex? You might look at this and go, well, it's only 3 things going to 2 things. So how can we look at a reaction and automatically know it's got to be complex? First, let's look at the exponents in the rate law. Here, this exponent is a 1, and H2O2's exponent is a 1. The exponents in the rate law do not match the stoichiometry. This is a 2, this is a 1, so that matches, but this is a 2 and it's not even in there. Okay? If it's a simple elementary reaction, they should match. But in this case, the exponents don't match. So because they don't match, that should give us a sign. Also, another way to kind of know that this is going to be complex is let's look how many reactants I have. So let's total it up. Not how many different things, but total reactants. So I have 2 reactants here, I have 1 reactant here, and I have 2 here. That's a total of 5 reactants. Now, when we're thinking about what happens, we said for a reaction to happen, you have this one thing colliding with another thing. So think about like our bumper cars. This bumper car is going to collide with this bumper car, and that's our reaction. So what this looks like here is saying all 5 of these are going to react and hit each other to make that. That's not going to happen. 5 reactants do not collide together to form this massive transition state and then break apart. So you'd have to think about, 5 bumper cars hitting each other, all at the right amount of energy, all at the right orientation to make this massive, big, globed up transition state, and then they're gonna break apart into I2 and 4 H2Os. It's not really gonna happen, okay? You're gonna have one thing decomposing, or you're gonna have 2 things hitting each other. We're not gonna have 5 things hitting each other. So the fact that we have 5 different things here should really be the way we kind of see that this is not gonna be nice and pretty and simple. All right, so now we know it's complex, which means it's gonna have a bunch of steps. So if it's got a bunch of steps, how do we write that out? How do we look at that? So if it's gonna be a list of steps, and I wanna show that, that is called a reaction mechanism. Okay, so here's my overall reaction that we just looked at. These would be all the steps. So this is my mechanism. These are the steps to get to that big one. You're not gonna have to write out these steps, okay? So don't sit here and freak out. How do I know that this is the first step? And how do I predict that? That would be organic, okay? So you're not gonna have to write this out. You just have to know if it's complex, it takes steps. You don't know if it takes 1 step or 2 steps or 3 steps, we don't know, okay? You won't have to know that. All we have to know is that this guy, our overall reaction here, is complex. So if it's complex, it takes a bunch of steps to get from my reactants to my products. So to get from here to here, it's going to take a lot of steps. These are my steps. Okay? These are my steps. If I add up my steps, like here's an I get this. Here's an H2O2. Here's 2 H3Os. If I add up my steps, remember Hess's law, if I can add up my steps, I'll get my overall. Okay, so here's my steps, here's my overall. Now, let's look at this. This is my reaction mechanism. Let's look at the parts of my reaction mechanism. Okay? Now, don't get thrown off by this. This is the same thing as H2O2. It's just showing how it's bonded. So sometimes it might be written kind of a little like that. So let's talk about a few terms related to my reaction mechanism. Anything that is made and then used up again, like this, it's made, and then used up, is called an intermediate. So if I make it in my reaction steps, if it's made somewhere and then immediately used up, it's an intermediate. Okay? It's not going to be a reactant, it's not going to be a product, it's going to be something made and then something used up. So HOI is an intermediate because I make it and then I get rid of it. All right, so let's look at this. Also, you'll notice that there's slow steps and fast steps. So that's going to be important in 2 slides when we talk about what that means from an overall standpoint. Why is it slow? Why is it fast? What does that mean? All right, so this is just kind of showing you what's happening. So remember, this guy and this guy is going to collide, make a transition state. Then that forms my new products. Then these 2 are going to collide, make my transition state, make my products. More collisions, make my products. Okay? So this is kind of what's happening at the molecular level, just so you can see that these are the steps This is my reaction mechanism, my steps to get to my end product. All right, now, how do I know how fast this is gonna go? I've got all these steps here. How do I know how fast it's gonna be? I've got some that are slow, some that are fast. So what determines how fast this whole reaction goes is based on this slow step, okay? So the slowest step in the sequence is what we call my rate limiting, or you might see it as rate determining. So rate limiting or rate determining step. So this is the one that's going to determine how fast the overall reaction is, because it's the slowest one. So the slowest step in the sequence, which you don't have to know yourself, it's going to tell you on your arrows here which one's fast, which one's slow, so you don't have to be able to predict that. So the slowest step in the sequence is your rate determining or rate limiting step. So the overall reaction rate is limited by the rate of the slowest step. All right, so let's look at this example. So here's a good analogy. So say I'm going to the supermarket and I need to run in. I can park my car and I can run really fast. Then I can run up to the item, grab my item, I can run up to the checkout line. But then I have to wait in line, and I have to wait in line, and I have to wait in line, and I have to wait in line. So the thing that determines how long it took me in the grocery store is how long I had to wait in the checkout line. So my slow step is my rate determining step. Okay? That's the step that determines how fast the reaction is. In a reaction, my slow step could be thousands or even a million times slower than the fast step. So my fast step could be like boom, boom, boom. But my slow step could be really, really slow. So this is why some reactions are really slow from an overall standpoint, even though they might get going from the get-go. So let's look at this. So here's my reaction. Step one was my slow one. So this determines the overall rate. The other two steps were fast. So they do not affect it at all. So if I'm trying to write the rate law is going to be determined by only my slow step. So I say rate is equal to K times concentration of the first. And because there's a 1 in front of here, I know it's going to be to the 1. Times the concentration in the second. I know there's a 1 here, so it's to the first. So that's going to be my rate law. I can only write this for elementary. Okay? I see how I use the stoichiometry to get my M and N here from the stoichiometry and the reaction. You can only do that if it's an elementary reaction. If it's complex, you can't do that. Only for elementary. All right, so let's summarize this. The rate law for an elementary, a nice, simple, easy reaction, can be determined from the stoichiometry. So if it's unimolecular, it's a 1. If it's bimolecular, it's a 2. Either the A to the second, or you've got your A and your B. You can't work backwards. I can't look at the rate and know it's elementary, okay? I can kind of check to see if it's complex that way, but I can't for sure. So if a rate law matches the stoichiometry, the reaction is elementary or complex. If it doesn't match, then I automatically know it's complex. But if it does match, it still could be complex, and I just got lucky that it matched up. Okay? Remember, a reaction must be complex if it doesn't match the stoichiometry, if we have a non-integer. So if we have like my M is 1/2, or if my N is like a negative 1/2, then I know it's going to be that. Or if the overall order is greater than 2. So if I have an overall order of 3 or 4, then it has to be complex, because then I have too many things reacting together for it to be a simple, easy thing. Okay? Now, you just kind of have to know definitions on this. I'm not going to make you write out reaction mechanisms or anything like that. You just kind of need to know the terms for today. Okay? I'm going to post one more lecture video where we're going to start talking about catalysts. So make sure you click on that link and watch your catalyst lecture video. Have a great day.